On March 1st, 2023, Tesla made a statement that sent shockwaves through the rare earth industry. At Tesla's Investor Day in Texas, Colin Campbell, Tesla's Vice President of Powertrain Engineering, announced that the company had designed its next-generation permanent magnet motor to use no rare earth materials at all. He showed a slide comparing the new motor with the one used in the Model Y. The existing motor used 3 rare earth elements, around 500 grams of one and about 10 grams each of 2 others. According to Tesla, the next-generation motor would use 0 grams of all 3. The reaction was immediate. Shares of Chinese rare earth mining companies dropped as investors considered what a rare earth-free Tesla motor could mean for future demand. One sentence and one slide had moved an entire mining sector. But more than 3 years later, the story is very different. As of early 2026, Tesla has not publicly demonstrated a production drive unit that completely eliminates rare earth materials. Even the latest high-performance Model Y still uses permanent magnets linked to a supply chain heavily dependent on China. So why is eliminating rare earth magnets from an electric motor so difficult? The answer begins with Tesla's history. The company is named after Nikola Tesla, whose work helped develop the AC induction motor. Unlike a permanent magnet motor, an induction motor does not need permanent magnets on its rotor. Instead, the stator creates a rotating magnetic field. That field induces an electrical current in the rotor, which creates its own magnetic field and makes the rotor spin. The biggest advantage is simple: no rare earth materials are needed. Tesla's original Roadster used an induction motor, and the Model S also relied on this technology. For years, Tesla built its vehicles around a motor that required no permanent magnets. Then came the Model 3 in 2017. Tesla switched to a permanent magnet motor. Instead of generating magnetism inside the rotor using electricity, the rotor contains permanent magnets, typically made from neodymium iron boron materials. The reason was efficiency. An induction motor has to spend some of its electrical energy creating the rotor's magnetic field. A permanent magnet motor already has that magnetism built in, allowing more of the battery's energy to be converted into motion. That can mean better efficiency, strong low-speed torque, and more range from the same battery. For Tesla, which was trying to build affordable electric vehicles with longer range, the benefits were too important to ignore. The rest of the EV industry moved in a similar direction, making permanent magnet motors extremely common. But there was a hidden price. High-performance permanent magnets require rare earth elements, especially neodymium. And the biggest problem isn't simply where the minerals are mined, it is where they are processed. Rare earth deposits exist in many countries, but China has built a dominant position in refining, processing, and manufacturing high-performance permanent magnets. So even if an automaker obtains rare earth ore from outside China, it may still depend on Chinese processing or magnet production. A decision made mainly for efficiency in 2017 had quietly created a major supply chain dependency. At the time, automakers were focused on range, performance, cost, and battery efficiency. Few people were thinking about how important rare earth materials would become as electric vehicle production expanded. By 2023, however, the situation had changed. Tesla wanted to keep the advantages of a permanent magnet motor while eliminating its dependence on rare earth materials. That is much harder than it sounds. A motor must deliver high power and torque while remaining efficient, compact, affordable, reliable, and durable. Removing rare earth magnets can affect several of these factors at the same time. Tesla therefore faces a difficult engineering challenge. Build a motor that performs like a modern permanent magnet motor without depending on rare earth materials. The irony is that Tesla once had a technology that already solved the supply problem. Its early vehicles used induction motors with no permanent magnets. But Tesla moved away from them because permanent magnet motors offered better efficiency for the company's long-range EV strategy. Now, Tesla is effectively trying to combine the best features of both approaches, permanent magnet-level performance and efficiency, without the rare earth dependency. That is why the 2023 announcement was so significant. Tesla wasn't simply promising another improvement to its electric motors. It was attempting to solve one of the biggest strategic problems facing the EV industry. But designing a prototype is only the beginning. The real test is whether Tesla can mass-produce a rare earth-free motor that is affordable, reliable, compact, powerful, and efficient enough to compete with today's best motors. Until that happens, the rare earth problem remains one of the toughest engineering and supply chain challenges in the electric car industry. Tesla is essentially trying to reverse a decision it made years ago without losing the efficiency that made permanent magnet motors so attractive. That is much harder than it sounds. The core problem is simple. A permanent magnet motor is only as good as the magnet inside it, and the strongest magnets rely on rare earth materials whose supply chain is heavily controlled by China. Consider ferrite magnets, one of the most obvious rare earth-free alternatives. Compared with the powerful neodymium magnets used in modern EV motors, ferrite magnets are dramatically weaker. Their maximum energy product is roughly 1/9 as high, while their resistance to demagnetization is also significantly lower. That creates a huge engineering challenge. Tesla cannot simply replace a strong neodymium magnet with a weaker ferrite magnet and expect the motor to perform the same way. The difference has to be compensated through the design of the entire motor. There are several ways engineers can do that. The first is geometry. If the magnet is weaker, you can increase the area over which its magnetic field is being used. One of the most important areas inside a motor is the air gap, the narrow space between the spinning rotor and the stationary stator. Engineers working on rare earth-free motor designs have found that weaker magnets often require a different motor geometry. Instead of simply changing the materials inside the existing motor, the shape and proportions of the motor itself may need to be redesigned. The second option is speed. Motor power depends on both torque and rotational speed. If a weaker magnet produces less torque, increasing the motor's rotational speed can help recover some of that lost power. This is where Tesla's high-speed rotor technology becomes important. In 2021, the Model S Plaid introduced a motor with a carbon fiber sleeve wrapped tightly around the rotor. The purpose is to keep the rotor stable as it spins at extremely high speeds. When a rotor spins faster, centrifugal forces try to push its components outward. The carbon fiber sleeve holds everything together and prevents excessive expansion. That allows the motor to operate at higher rotational speeds without becoming structurally unsafe. The technology also helps maintain a more precise gap between the rotor and stator. Keeping that gap under control is important because the magnetic field becomes more effective when the motor's geometry is tightly controlled. There are thermal benefits as well. Carbon fiber behaves differently from metals when it comes to heat transfer, which can help protect sensitive components inside the rotor. Heat is one of the biggest limits on electric motor performance. When a motor operates under heavy load for a long period, its temperature rises. Eventually, the vehicle's control system has to reduce power to prevent damage. A motor that can better control heat can maintain high performance for longer. However, Tesla's carbon fiber rotor should not be viewed as a completely new invention. Retaining sleeves have been used in high-speed electric motors before. Tesla's achievement was largely in adapting the technology for automotive mass production, while making it reliable and cost-effective enough for a production vehicle. That is an important distinction. It is primarily a manufacturing achievement, rather than a breakthrough in the basic physics of electric motors. The third part of Tesla's strategy involves everything around the motor. Tesla has indicated that its next-generation drive unit would use substantially less silicon carbide in its power electronics, support different battery chemistries, and take up much less factory space to manufacture. This reveals the bigger picture. Tesla isn't relying on one secret trick to eliminate rare earth materials. Instead, it is combining multiple engineering improvements. The company can redesign the motor's geometry, increase rotational speed, strengthen the rotor, improve thermal management, optimize the power electronics, and simplify manufacturing. Each improvement can help compensate for the limitations of weaker or alternative magnets. Ultimately, Tesla's challenge is not simply to build a motor without rare earth materials. It needs to build one that remains powerful, efficient, compact, reliable, affordable, and easy to manufacture at enormous scale. That is what makes the rare earth problem so difficult. Removing the rare earth magnet is only the first step. The real challenge is replacing everything that magnet gives the motor, without giving up the performance that made permanent magnet motors so valuable in the first place. Tesla is trying to solve a difficult problem: how to reduce or eliminate rare earth materials without giving up the efficiency and performance of permanent magnet motors. The solution is not one simple invention. Tesla can compensate for weaker magnets through better motor geometry, higher rotational speeds, improved cooling, and smarter electronics. But all of these changes have to work together, which explains why the process has taken longer than many expected. The difference between Tesla's 2023 announcement and what it delivered in 2026 is important. The 2026 Model Y Performance uses Tesla's latest motor technology and delivers impressive numbers. It produces around 510 horsepower, compared with about 456 horsepower in the previous generation. Tesla claims a 0 to 60 miles per hour time of roughly 3.3 seconds, with a top speed of about 155 miles per hour and a quarter-mile time around 11.5 seconds. But the most interesting detail isn't the horsepower. The front motor is an induction motor, while the rear motor is a permanent magnet synchronous motor. That combination is intentional. Induction motors don't require permanent rare earth magnets, and Tesla has used them for years. They are particularly useful when a vehicle needs a large amount of power for short periods. The permanent magnet motor, meanwhile, is more efficient for everyday driving. So Tesla effectively uses two different technologies for two different jobs. The front motor provides additional power when needed, while the rear permanent magnet motor handles much of the car's normal driving efficiently. The battery has also improved. The new Model Y Performance uses a battery pack in the low 80 kilowatt-hour range, with newer cells offering higher energy density. The result is impressive: around 306 miles of EPA range, more than 10% better than the previous performance model, despite the increase in power. Charging can reach roughly 250 kilowatts, and the starting price is just under $60,000. So Tesla delivered more power, more range, and a lower price. That is a significant engineering achievement. But it is not the rare earth breakthrough many people expected. Tesla improved the motor's performance and efficiency, but it did not publicly demonstrate that it had completely eliminated rare earth materials from its main permanent magnet drive unit. And then the supply chain problem became even more serious. In 2025, China introduced export controls on several heavy rare earth elements and the permanent magnets made from them. The biggest concern wasn't simply higher prices. It was uncertainty. Automakers in the United States and Europe had to deal with licensing and supply problems. For a car factory, even a temporary shortage of one critical component can stop production. A vehicle contains thousands of parts. If the magnets needed for a drive unit aren't available, the factory cannot simply build the car without them. Later in 2025, China announced even broader restrictions that could potentially affect foreign-made products containing very small amounts of Chinese rare earth materials. The impact could extend far beyond electric vehicles. Motors, speakers, sensors, and many other modern technologies depend on rare earth materials somewhere in their supply chains. Those broader restrictions were later suspended for a year as part of a wider trade agreement. But suspended does not mean permanently removed. Automakers therefore still have to prepare for the possibility that similar restrictions could return. And that changes the importance of Tesla's 2023 announcement. At first, a rare earth-free motor looked mainly like an engineering and efficiency project. Now it looks more like supply chain insurance. Tesla isn't simply trying to make a cleaner motor or create another marketing advantage. It is trying to eliminate a major point of dependence that could potentially be controlled by another government. Yet the biggest question remains unanswered. More than 3 years after Tesla showed its famous Investor Day slide promising a permanent magnet motor using zero rare earth materials, There is still no publicly confirmed evidence of a mass-produced Tesla drive unit that fully achieves that goal. Tesla has clearly improved its motors, electronics, batteries, and manufacturing. But the rare earth-free production motor that attracted so much attention in 2023 remains the part of the story Tesla has yet to conclusively deliver. Tesla has never announced a definite production date for its rare earth-free permanent magnet motor. For now, it remains an engineering target rather than a publicly confirmed production product. The reason goes back to the huge performance gap between rare earth magnets and alternatives such as ferrite. Ferrite is one of the most obvious replacements because the technology is already proven. General Motors used a ferrite-based permanent magnet motor in the second-generation Voltec powertrain of the 2016 Chevrolet Volt. More recently, Japan's Proterial has demonstrated ferrite-based electric motor designs. One of its motors reportedly achieved similar power and maximum speed to a comparable neodymium motor. But there was a major compromise. The ferrite motor was about 30% heavier. That is a serious problem for an electric vehicle. Every extra kilogram affects efficiency and range remains one of the most important factors when people compare EVs. So while ferrite can eliminate dependence on rare earth materials, the added weight can reduce the very efficiency that manufacturers are trying to maximize. That is the fundamental challenge. The alternative works, but it can cost you the performance advantage. There is another pressure that received little attention in 2023: humanoid robotics. Humanoid robots require compact, high-torque motors at almost every joint. To produce a lot of torque from a small actuator, powerful permanent magnets are extremely useful. If robotics grows as quickly as many companies expect, demand for high-performance rare earth magnets could actually increase. That would make the transition away from rare earth materials even more difficult. So, after 3 years, the honest assessment of Tesla's position is complicated. Tesla identified the problem early, publicly warned about rare earth dependence, and pushed the industry to take the issue seriously. But when the company tried to eliminate rare earth materials completely, it ran into the same basic physics that everyone else faces. That does not mean Tesla made no progress. At its 2023 Investor Day, Tesla said it had already reduced the rare earth content of the Model 3 powertrain by about 25% compared with its 2017 design. That was a real reduction already being delivered in production. Tesla's use of induction motors is another example. Its dual-motor vehicles already use an induction motor on one axle, meaning part of the propulsion system does not rely on permanent rare earth magnets. The company's carbon fiber rotor technology is also real. Whether or not it deserves to be called revolutionary, Tesla developed the manufacturing equipment needed to produce the technology at automotive scale. That is a significant manufacturing achievement. Tesla also deserves credit for recognizing the strategic risk early. The company highlighted rare earth dependence before China turned the issue into a major supply chain and geopolitical concern. What looked like a minor problem to many people in 2023 became much more important later. There is also a reasonable argument for why Tesla has not rushed its rare earth-free motor into production. Imagine replacing a proven motor with a significantly heavier alternative simply to avoid rare earth materials. That could solve a supply chain problem while creating a performance problem for the customer. From an engineering perspective, waiting until the alternative can compete on weight, efficiency, cost, power, and reliability may actually be the smarter decision. So the verdict is not simply that Tesla succeeded or failed. Both things are true. Tesla identified the right problem, but the expected timeline proved far too optimistic. And Tesla is not alone. BYD has built a highly integrated manufacturing system covering batteries, motors, and semiconductor technology. That gives the company a major advantage, but building its own motors does not automatically eliminate dependence on rare earth materials. The question is still where the magnet material comes from. Toyota has focused on reducing or redistributing the use of the most supply-sensitive rare earth elements rather than eliminating rare earths completely. Hyundai has taken a different approach, investing heavily in technologies such as 800-volt electrical systems and faster charging. Those improvements can make EVs better without directly solving the rare earth problem. Smaller companies are also experimenting with motors that create magnetic fields through electrical control, rather than relying entirely on permanent magnets. But the goal for all of these efforts is the same. It isn't enough to build a motor without rare earth materials. The real challenge is creating one that matches today's best motors in power, efficiency, size, weight, cost, durability, and reliability, while also being practical to manufacture at massive scale. Until those requirements can all be met at the same time, rare earth magnets will remain one of the hardest technologies in the electric vehicle industry to replace. The odds of completely replacing rare earth magnets are still challenging, but the fact that so many companies are trying tells you just how valuable the solution could be. Almost every major automaker is approaching the problem differently, but the goal is similar. More range from every unit of electricity, less dependence on vulnerable suppliers, and lower manufacturing costs. The company that solves all three problems first won't simply win a comparison based on horsepower or range. It could also remove a major supply chain weakness that another government currently has the ability to influence. And this matters even if you have no interest in buying a Tesla. There are three practical lessons worth remembering. First, pay attention to the production timeline, not just the announcement. When a company introduces a new technology without providing clear production data or a firm launch date, the missing timeline can be more important than the technology itself. Tesla's zero rare earth motor is a good example. More than 3 years have passed since the announcement, yet there is still no confirmed mass production version. That gap tells us something important about how difficult the technology really is. Second, don't judge EV efficiency by battery size alone. If you're comparing electric cars, motor technology can be just as important as the battery pack. Two vehicles can have batteries of similar size, but deliver noticeably different real-world range because their drive units convert electricity into motion with different levels of efficiency. So, when you look at an EV's range, remember that the story isn't only about the battery. The motor matters too. Third, pay attention to supply chain news. Changes in raw material policies can reach consumers much faster than most people expect. When China introduced rare earth export controls in 2025, automakers quickly faced production and supply problems. A shortage of a critical component can affect vehicle availability and delivery times even when customer demand hasn't changed. That leads to a broader rule. Every efficiency improvement has a supply chain behind it, and as manufacturers search for better performance and efficiency, they can sometimes become more dependent on a smaller number of specialized suppliers. The best materials often come from the fewest places. That is the trade the EV industry made while racing to improve efficiency. Now, the industry is trying to reverse that dependence without sacrificing the performance gains it already achieved. So where does that leave Tesla? Was its zero rare earth motor a genuine long-term engineering goal that simply proved much harder than expected? Or was the original timeline far too optimistic from the beginning? That's the interesting question. And there's one Tesla vehicle where everything we've discussed becomes even more important: the Cybercab. This entire story has focused on getting more distance from every unit of electricity. The Cybercab takes that idea to an extreme. Tesla has targeted a relatively small battery, less than half the size of the Model Y Performance's pack, while still aiming for roughly 200 miles of range. For a robotaxi, efficiency is especially important. A vehicle that operates throughout the day only makes economic sense if it spends as little time as possible sitting at a charger. The charging system itself is also interesting. Tesla originally said the Cybercab would have no traditional charging port and would rely entirely on wireless charging. The idea is simple. The vehicle parks over a charging pad, charges automatically, and doesn't require anyone to plug in a cable. But later, validation vehicles appeared with a conventional NACS charging port hidden behind a small door in the rear bumper. At the same time, Tesla received regulatory approval related to the wireless technology needed to help the vehicle align with its charging system. That creates an obvious question. Which charging system will actually make it into the final production vehicle? The answer could reveal how close the Cybercab really is to becoming a fully operational robotaxi, and it connects directly to everything we've discussed, from motor efficiency and battery size to manufacturing costs and supply chain dependence. The Cybercab isn't just another electric vehicle. It is Tesla's attempt to build a vehicle where every part of the system is optimized around one goal: moving people efficiently while spending as little time and energy as possible doing it. And that makes the technology behind its motor, battery, and charging system especially important. Because ultimately, the future of electric transportation won't be determined by one breakthrough. It will come from dozens of small engineering decisions working together, and from figuring out how to make those technologies affordable, reliable, and independent enough to survive the real world.